Hello everyone, my name is Juan José Toledo, and in this work we will talk about the characterization of some scintillator screens when they are irradiated by a cesium ion beam. We want to use this scintillator in the imaging heavy ion beam proof diagnostic that have been installed at the ASDEX Upgrade tokamak. This diagnostic measure the plasma density, the potential, and the magnetic field fluctuation at the plasma edge. And it does by injecting a primary beam into the tokamak. This beam is then ionized by the plasma, and the ionization creates a secondary beam. This secondary beam is then collected by a scintillator detector as in a fast ion loss detector. And the use of a scintillator is the main difference between this diagnostic and classical heavy ion beam proofs. On previous work, the study of ionoluminescence of scintillators was done when they are irradiated by light ion. So a characterization with heavy ion is needed, for example with cesium. The setup that we have achieved in order to obtain the characterization is the following one. The IHIP injector creates a beam that goes through a 1 mm collimator. This collimator allows us to decrease the incident current intensity, and then the beam goes into a vacuum chamber. This vacuum chamber has a black coating that minimizes the light reflection. The beam irradiates the scintillator, and the scintillator creates light by ionoluminescence. This light is then collected by an optical fiber that is connected to a spectrometer that allows us to measure lights in a wavelength range like this one. Also, we have a Faraday cap which allows us to measure the incident current. We have characterized 4 different scintillators: TG Green A, TG Green B, JAXI, and P11. These scintillators are nowadays used on some plasma diagnostic. For example, TG Green is used in the field diagnostic at ASDEX Upgrade tokamak. TG Green A and P11 have been coated by the sedimentation process at Centro Nacional de Aceleradores in Seville. This process consists in mix and phosphor powder and adhesive. Then we pour this mix over a metal plate and we create the scintillator. We have found here in the spectrum of the light emitted by the scintillator some differences between TG Green A and TG Green B. These differences could be explained by the composition of these scintillators, as we can see here. This composition was measured by energy dispersive X-ray spectroscopy. Also, a scanning electron microscopy analysis had been done in order to obtain information about the grain size of the scintillator. As we can see, JAXI have an order of magnitude higher grain size than TG Green B, and also its density is much lower. The first characteristic that we have measured is the yield dependence with incident ion energy. What is yield? Yield is the number of photons that a scintillator emits when it is irradiated by an ion. As we can see, TG Green A and TG Green B, TG Green A in red and also in brown, because we measure at two different positions of the scintillators, and TG Green B in yellow has the highest efficiency of the scintillators, and also P11 here in pink has the lowest one. When we increase the incident energy, we increase also the yield until we can see a decrease in the yield This decrease could be explained by the degradation of this scintillator. When a scintillator is irradiated by an ion fluency, this irradiation creates some damage in the structure of the scintillator, and this damage inhibits light. As we can see, thanks to the color bar, a first measure at 55 keV have much more yield than a second one measured at 55 keV after the scintillator suffers degradation. We can see at TG green A and at TG green B. In order to study this yield and independent wind energy when the scintillator is full damage, we have done this measure in a position where irradiation has created enough damage in the scintillator in order to don't inhibit more light, more efficiency. As we can see, when we increase the energy of the incident ions, we increase also the yield of the scintillator. The next characteristic that we have measured is the ionoluminescence degradation of the materials. As we have discussed, the materials suffer degradation when they are irradiated by incident ions. And as we can see in this picture, P11 suffers the fastest degradation, and TG green A and TG green B suffers the slowest one. We can explain this degradation by the Black-Bird model. The Black-Bird model explains that the initial luminescence and the luminescence after suffer a fluency F are correlated by this equation. This number here is the fluence that we need to irradiate to a scintillator in order to reduce its yield to a 50% its initial emission. We have done a linear fit between the first part of the equation, the left part, and the ion fluencies. As we can see, the slope is the inverse of this number that we have discussed earlier, and we can find that this number obtained by this slope, the slope of the linear fit, is very similar to the fluence at that we have irradiate to scintillators when the luminescence is at 50%, the initial luminescence, in this figure. Finally, the last characteristic that we have measured is the emission linearity with incident current. When we increase the number of incident ions that irradiate the scintillators, there are also an increasing of the emitted photons, and this increasing are a linear increasing. As we can see, a linear fit are very suitable. To sum up, TG green A had the lowest degradation and the highest yield. We need around 850 shots at the upgrade in order to degrade the ionoluminescence of TG green A at 50%, and also the emission of TG green A, TG green B, and Jesse showed a linear response with incident intensity current. That's all, and thank you very much.